All right, so welcome to Circuits 2. Let's talk about the syllabus and all that kind of fun stuff real quick. So I am Dr. Hartman. My office is upstairs here in Nethkin Hall. So if you leave this room and go into the stairwell that's on the other side of that chalkboard, my office is the first one on the left. My office hours for this quarter are going to be Tuesday and Thursday, 9 a.m. to 2 p.m. Um, My email address is just my last name at latech.edu, and there's my office phone number. Don't call it, just email me or ask me for my actual cell phone number and just text me. In the event that disaster, extreme weather event, etc., happens, the class is going to continue on via Canvas and Zoom. So I do have a Zoom link set up on our Canvas page and all of that kind of stuff. I am using it to record my lectures and everything for this class. Just as a heads up, I am in no way, shape, or form obligated to record these lectures. I am doing it simply as a courtesy. And so that means I will have them uploaded to my shitty YouTube channel whenever the hell I get around to it. Do not come harass me and be like, Dr. Hartman, when are you going to upload this lecture? Because I guarantee you that will add at least a day into when I get around to do it, because I am a spiteful asshole. Okay. So it'll get uploaded when I get around to it. Let's see. So course objectives, we are going to apply the knowledge we arguably gained in circuits one by analyzing more complex circuits, including basic amplifier circuits, resonator circuits, more sinusoidally excited circuits, and then polyphase power circuits. The official textbook for this class is Engineering Circuit Analysis 10th edition by Height, Kemmerly, Phillips, and Durbin. I hope none of you were dumb enough to actually buy that textbook. Since I'm recording everything, there's really no reason for you guys to have a textbook for this class, but if you want one, I have supplied a link for the textbook Circuit and Analysis and Design by Ulabi, Maharbis, and First here. If we click on this link, it literally just takes you to a free PDF textbook that you can download. This is actually a pretty good textbook. I use it for lots of classes and all that kind of stuff. So if you need or feel like you need a textbook, this is the one that I would actually recommend. A, because it's good, and B, because it's free. Okay. Let's go back here to the syllabus. Let's see, disability disclosure stuff. So students that need testing or classroom accommodations based on a disability must be registered with the Louisiana Tech University Office of Testing and Disability Services. You're encouraged to discuss your needs with me as soon as possible. If you do not have a current accommodation memo, visit the Office of Testing and Disability Services for assistance. For what it's worth, anything that you see in blue on this syllabus is a link, and I believe I checked them all, so they should take you where they're supposed to. The official class attendance policy is defined in University Policy 2206, which is available at that link. Attendance is going to be taken promptly at the beginning of class, and any student arriving after attendance has been checked without a reasonable excuse will be considered absent. All that kind of good stuff. Unofficially, you are adults. If you don't want to be here, that's your choice. Some days you might just not want to put on pants. I get it. There's a lot of days I don't want to put on pants. That's what the Zoom is for. So, do whatever you want to do. Let's see here. Academic honor code stuff. So in accordance with the academic honor code, students pledge, being a student of higher standards, I pledge to embody the principles of academic integrity. Then we have the university's official academic misconduct policy with a link to it, and then a little bit about behavior and cheating. With regards to the behavior, says students are expected to maintain a professional classroom environment. I'm going to use air quotes for professional here because many of you have had a class with me before, and you know that professional is not a descriptor you would use to describe how I handle my business. So if you're as professional as I am, we're going to be okay. Generally speaking, just don't be dicks to each other and it'll all work out okay. Cheating, don't do it. Really pisses me off. I will do anything and everything I can to get you kicked out of the university if I catch you cheating, just as a heads up. Let's see. Homeworks. So a selection of homework problems is going to be posted on the course's Canvas page at the end of most lectures. I think I have 18 different homework assignments created for this class. Homework assignments are due at 11:59 p.m. 2 class meetings after they are assigned and must be properly formatted as detailed on the course's Canvas page. And I'll show you what I mean by that in just a moment. Any homework assignment submission that does not adhere to the format detailed on the course's Canvas page will be rejected from grading. Late homework assignments will incur a 20% penalty for each day that they are late. So let me get out of this real quick and show you how I want your homeworks formatted. I am the nitpickiest of assholes about your homeworks. I just want to be very, very clear about that. So I want them done in a very, very specific format. And if you do not do it in the very, very specific format that I want, you will lose points. After homework 3, if you can't turn it in the correct format, you just get a 0 because I don't want to deal with your bullshit anymore. Okay. So here is a homework formatting example. So this is a solution to an old homework 1 in this class, and I have it formatted the exact way that I want it. So you'll put your name up here, your campus-wide ID. This is just the assignment sheet. Yes, I am aware that I misspelled the word answer and I was too lazy to correct it for what it's worth. So the first few pages of the homework are literally just the assignment sheet, okay? Notice that I have the marks here. So, this is, scroll better, page 1 of whatever, 2 of whatever, all of that kind of good stuff. Then we get into my solution, okay? I'm on engineering paper here. I want you to submit your work on engineering paper. I will upload some digital engineering paper for you guys to use that have tablets if you want it. If not, you need to go on to the university bookstore or probably Amazon where it's cheaper and just buy a pad of engineering paper, okay? So here is the problem statement rewritten, the whole damn thing. Then I get into my solution, and you don't have to do this granular of detail, but I usually write out what I'm doing so that somebody could follow my work. So I was writing it with the intention of the grader being able to follow my work. You guys should write it with the intention of the grader being able to follow your work so that they can make sure what the hell it is that you're doing, okay? Yeah, it isn't Ashton. It'll be somebody else. Box your final answer, please. You don't have to do this +2 and +1 thing. That's me telling the grader how many points should count for this thing. So that's a way for me to let you know that units absolutely matter to me. And if you don't put units on there, you will be consistently docked points. You should be using units throughout all of your calculations, not just tacking that shit on at the end. So there's my handwritten work for part A, then handwritten work for part B, handwritten work for part C, etc. And then after all of my handwritten work for problem 1, I have my computer work for problem 1, which I used MathCAD to do some things for this particular problem. Then we have handwritten work for problem 2 in proper engineering format, and then computer work from problem 2, and so on and so forth. So that's how I want it. All of the assignment sheet will essentially be cover pages for the actual assignment. Then give me your work for problem 1 in correct engineering format, and then any computer work for problem 1. Then your work for problem 2 in engineering format, and then any computer aided work for problem 2, and so on and so forth for every single assignment, okay? Not all problems will require the use of a computer algebra tool or a circuit simulation, but many of them will. So if you have any questions about things before you turn it in or whatever, by all means, please ask. You will get some feedback on the first few homework assignments about how to correct the format and stuff. But like I said, after homework 3, you either turn it right, turn it in correctly, or you shouldn't even bother doing it at all. Any questions about the homework formatting? Yes.
Does it have to be written by hand?
Yes. Well, actually, rewriting the problem statement. So I will provide you with a Word document version and a PDF version. So you can just cut that and paste it in if you want to. I will allow you to do that. But all of your work, I'm expecting it to be written. But for rewriting the problem statement stuff, I'm okay if you have a digital version of that. Yes.
You have to use engineering.
You do.
Correct.
Yep. All right, let's get back to the syllabus. Exams. So there are going to be 4 exams giving during this course. Each exam will have 2 parts. There will be a multiple choice closed book and closed notes portion that is worth 70% of your exam grade. So think similar to what you guys did in Circuits 1. And then there is going to be an open book slash notes slash internet, whatever portion, um, where you have to use either MathCAD or LT Spice or something like that to answer some stuff. For what it's worth, I know that some of you guys prefer to use Wolfram Alpha or whatever as your computer algebra tool. I don't care. I'm testing you on your ability to use MathCAD. So if you don't use MathCAD, you're getting a 0. So use MathCAD because it's what was provided to you. For the in-class portion of the exams, only FE approved calculators are permitted for use. So these are the same calculators that you were allowed to use in Circuits 1, so I won't go on my normal calculator rant on that kind of stuff. All of the in-class portions of the exams will have a no cell phone policy. So any cell phone seen or heard at any time during the exam will result in an automatic 0. Let's see. So how the grades for this class are broken down. Homework is 20%, exam 1 is 20%, exam 2 is 20%, exam 3 is 20%, exam 4 is 20%. So everything is just weighted equally there. It says here all homework assignments and design project assignments are weighted equally. So that is a artifact from my prior times when I've taught this class where I had specific design projects. Those are integrated into your homework assignments now. So you're still doing them, they're just not their own thing. The grading scale used for this course is a traditional 10-point scale where anything above a 90% is an A. 89.99 down to 80.00 is a B. I am an asshole. I don't round up. So if you want to earn an A in this class, make above a 90. The last day a student can drop a course for the winter quarter in order to get a W is Friday, February 6th, 2026. Let's see, the contents of this syllabus are not expected to change. I might update it to get rid of the design project thing. Might be lazy and just leave it there since I've explained it away. But I reserve the right to change the syllabus if I feel it's necessary, as long as I tell you what I'm doing and all of that kind of good stuff. Looks like I accidentally copy pasted this thing twice. Emergency notification system stuff, sign up for it. We've all been here, or maybe you guys haven't been here long enough, but Ashton and I have been here long enough to realize that there are going to be some days where the weather just looks like it's going to be gross and classes are going to be canceled, and you probably want to know about that because I know when I wasn't signed up for it and I showed up to class on a day where I didn't have to, I was furious. So anyway. Let's see, COVID-19 policy. This is just a general sickness policy. If you're sick, attend over Zoom. Don't come here and get everybody else sick. If you get me sick, I'm going to be furious. For what it's worth, last winter quarter, I somehow managed to get strep throat and COVID. So it's going to be hard to top that on how pissed off I can get. So that, and I also gave Ashton COVID, like, wasn't going to mention, wasn't going to mention that. Charlie's fine. Didn't murder any babies or anything like that. But yeah. Um, so don't get me sick because I go to lunch with people who are dumb enough to have children. But anyway. Okay. Wow. I wish I hadn't recorded me saying that. Counseling services. Students have access to confidential counseling services at no additional cost to you. This is already handled as part of your fees and everything. Visit the Louisiana Tech Counseling Services website to learn more. Here's the university's official non-discrimination policy. So Louisiana Tech is committed to the principle of providing the opportunity for learning and development of all qualified citizens without regard to race, color, national origin, religion, age, sex, sexual orientation, marital status, or disability. Persons with concerns about being discriminated against should contact the Director of Title IX Compliance. That is Miss Mortissa Harvey. So her name is here. Her office is in Wiley Tower 1536. This is her phone number, and this is her email address. In addition to being Title IX compliant, Louisiana Tech is Section 504 compliant, where Section 504 is a federal law designed to protect the rights of individuals with disabilities in programs and activities that receive federal financial assistance from the U.S. Department of Education. Persons with concerns about Section 504 compliance may contact the Section 504 coordinator. That is Miss Annie Jantz. Her office is Keeney Hall 305 as part of the Division of Student Affairs. Her phone number and her email address are also provided to you. And then just a general, if you have need help with Canvas and or Workday, which we all do at times, please direct your questions or problems to the Computing Center Help Desk. The link here should take you directly to their website. I've also provided you with their email address as well as their phone number. And then lastly, because we have some design projects and stuff in this class that you could arguably use AI in some way, shape, or form to assist you with those, I want to explicitly tell you what my AI policy is in this class. So you are allowed to use AI to help generate ideas or as a creative catalyst for the projects. You can use AI tools to enhance your learning about fundamentals and all of that kind of good stuff. You can use it to assist you with solving problems, and you can use it to help you with any writing, which there's not a whole hell of a lot of writing in this class. You cannot use it to just do the work for you, and all of that kind of good stuff. And you can't use AI during any of the exams or anything like that. Okay. If you do choose to use AI for any part of your thing, simply cite it and we're okay. Okay. So just let me know. It's not a big deal. And then here we have our tentative course schedule. And wow, you guys are going to hate the places that I've put the tests. So exam 1 is on the day we get back from Christmas holiday because there was no better place to put it. Okay. Exam 2 is the day we get back after the brief Martin Luther King Jr. holiday. And then exam 3 is on a relatively normal date. And then exam 4 is on literally the last day of the quarter because we have a lot of stuff that we have to talk about here. So those are when the tests are. Manage your time accordingly. Anybody have any questions, comments, or concerns about the syllabus? Okay, so today I want to introduce you guys to circuit simulation. So before we do that, I want to work a brief problem with you, okay? So I've just got a random circuit analysis textbook, and this first problem that we're going to look at is just finding the Thevenin equivalent network of a particular circuit, okay? So I've got a circuit here containing a 1 amp current source connected in parallel to a 6 ohm resistance. Then we've got over here a 12 volt source. Here is another 6 ohm resistor. Down here on the bottom is a third 6 ohm resistor. And then off to the right, I'm going to draw a set of terminals. So this will be terminal A and terminal B. Okay. And so, as I mentioned a moment ago, our goal here is to determine the Thevenin equivalent circuit. So I'm going to say explicitly that I want us to find the Thevenin voltage, VTH, the Norton current, I Norton, and the Thevenin resistance, RTH, with respect to terminals A and B. So let's start with finding VTH. How many of you, or can any of you, or might be a better way to phrase this, tell me what the Thevenin voltage is? I'm not looking for a numerical answer, obviously, yet, but how do I find the Thevenin voltage when I've got a network with a set of terminals? So it is a voltage drop across those open circuited terminals, right? A Thevenin voltage by definition is the open circuit voltage measured across the terminals of a network, okay? I'm going to choose to put my positive polarity at terminal A and my negative polarity at terminal B because I didn't specify it. I'm just telling you what I'm doing. So this is the circuit that we are going to analyze really quickly, which I'm just redrawing the exact same circuit, but I'm just going to define that VTH. While I'm redrawing the circuit, I'd like for you guys to think about what analysis method or methods might be used in order to determine this quantity. So this is the VTH that I'm trying to find. And that's another 6 ohm resistor. All right. So what circuit analysis techniques might we use to find this VTH? Anybody have any thoughts? KVL, okay. Explain yourself further, please.
Since we have the voltages, we can do KB on the right. We'll try across like
So the Thevenin voltage is going to be the voltage drop across the rightmost 6 ohm resistor for sure. For what it's worth, with me looking at this, I don't see anything that's like a super easy and trivial way to do this, right? So I don't see any way without using superposition that I could do this using just like Ohm's law, KVL, KCL, voltage division, current division. So using superposition, I could use those things, but that means I have to work the problem twice, and I'm lazy and I don't want to do that. So I would probably wind up using nodal analysis or mesh analysis here because this is complicated enough to justify that, at least in my thought process. So because I'm finding Thevenin voltage, I would probably use nodal analysis because that's just going to give me voltages directly, so I don't have to do any extra work at the end to sort that out, okay? So let's say that we're going to use nodal analysis. Just to refresh you guys on the concept of supernodes, I'm going to choose to put my reference or ground here at the negative polarity terminal of VTH instead of at one of the nodes that are touching the voltage source. So I'm going to force myself to deal with a supernode just to refresh you guys on how that works. Okay. So I'm going to label my other nodal voltages here really quickly. So I'm going to have some nodal voltage. Let's call this V1 at this node. I'm going to have some nodal voltage V2 at this top right node. And I'm going to have some nodal voltage V3 at this bottom left node. So I've got a 3-equation, 3 unknown system. And hopefully we can all see very easily that if I solve for the nodal voltage V2, that is the same thing as the Thevenin voltage that I'm trying to find, okay? So applying, let's say, I'm going to have a voltage relationship equation. So I've got my 12-volt source, and that is going to be equal to what combination of nodal voltages? V2 minus V1, absolutely right. Since I only have the one voltage source, that's the only voltage relationship equation I'm going to have. Now I'm going to write my KCL at supernode 1, 2. So for what it's worth, I'm just going to be adding this current plus this current plus this current together, right? So KVL at supernode 1, 2. Yes, that's right, KCL, sorry. So that's going to look like 1 amp plus V1 minus V3 over 6 ohms plus V2 over 6 ohms is equal to 0. And then lastly, I'm going to have to apply KCL at node 3. So that's going to be this current plus this current plus this current added together. So that's going to look like negative 1 amps plus V3 minus V1 over 6 ohms plus V3 over 6 ohms is equal to 0. And I now have 3 equations for my 3 unknown systems, so I can throw this into a system solver. I brought my trusty TI-36, so I'm going to go ahead and solve for this thing. Okay. So throwing this into my system solver, in my first equation, my coefficient for V1 is -1, my coefficient for V2 is +1, my coefficient for V3 is 0, my constant term is 12. In my second equation, my coefficient for V1 is 1 over 6, my coefficient for V2 is 1 over 6, my coefficient for V3 is -1 over 6, and my constant term is -1. In my third equation, my coefficient for V1 is -1/3, excuse me, 1/6. My coefficient for V2 is 0. My coefficient for V3 is going to be 1/6 plus 1/6, which is 1/3. And my constant term is going to be +1. So when I solved this system of equations, if I put everything in my calculator right, I got the nodal voltage V1 to be -10 volts, the nodal voltage V2 to be +2 volts, just for what it's worth. This is the same thing as VTH. And lastly, the nodal voltage V3 came out to be -2 volts. Moving along, our Norton current. So how do I find that? Anybody remember? Short circuit the terminals, and then I'm finding the current that's flowing through the short. Absolutely right. So redrawing my circuit. So here is my open circuited set of terminals. I'm simply going to short that out. Because I found the Thevenin voltage with the positive polarity on top, I need to find my Norton current flowing down because it should be flowing into wherever the positive polarity terminal of VTH was. Since I'm finding a current, I'm going to just use mesh analysis to make my life easier, right? So I'm going to have this mesh current, which I'm going to call I1, and this mesh current that I'm going to call I2. For what it's worth, I'm making this larger combination of things a single mesh because that short-circuited set of terminals shorts out the 6 ohm resistor so I know no current's going to flow through that branch. So I can just keep that mesh current going around because I know nothing's going to branch off. Okay. So I have a current relationship equation. Where that's just going to be I1 is equal to what combination of, 1 amp is equal to what combination of mesh currents? Negative I1, absolutely right. And now I'm just going to have KVL around mesh 2. So that's going to look like 6 ohms times I2 minus I1 minus 12 volts plus 6 ohms times I2 is equal to 0. And I'm now just going to solve this simple system. I know that I could do this using substitution, but I am also bad at substitution and incredibly lazy, so this is going to go into the calculator as well. Okay. So I've got a 2x2 system solver. Shit, press the wrong button. So in my first equation, my coefficient for I1 is -1. My coefficient for I2 is 0. My constant term is 1. In my second equation, my coefficient for I1 is -6. My coefficient for I2 is 6 plus 6 is 12. My constant term is +12. So solving this, I get I1 is -1 amp and I2 is 1/2 of an amp, where I2 is the same thing as I Norton by inspection. Okay. Putting these two results together, I'm just going to do this kind of over here because I'm running out of space on this page. Our Thevenin resistance could be found using resistance combination techniques by looking at the dead network. But another way to do it would be to simply take the ratio of VTH to I Norton, which in this case would be 2 volts divided by 1/2 an amp is going to look like 4 ohms. All right. So we very briefly reviewed Thevenin and Norton equivalent circuits, boring stuff that you guys have all done before. Now let's do the same thing, but using circuit simulation tools, okay? So I've got LT Spice opened up here, and I want to show you guys how to use it. So I just went and opened up a new schematic, okay? And I'm literally just going to redraw the exact same thing that we already had, okay? So I'm going to start with the current source. So in order to get the current source, I'm going to go over here to the component menu, okay? So that's the one that looks like an op amp. And for what it's worth, I just updated this thing yesterday, so my screen should look like your screen, or at least I hope it does. There is a keyboard shortcut for this, so I could just press the letter P and it will automatically bring up this menu, but I'm clicking it here, okay? So I'm going to look for a current source. I could literally look through all of this stuff, but I'm way too lazy. So instead, I'm just going to type the word current. And that will show me all of the options. And this is going to give me a current source, okay? So I'm going to just click OK and then place this somewhere on my field. And then I'm going to press the escape key so that I don't accidentally place down another one. Okay. So this is supposed to be a 1 amp current source. So in order to make this a 1 amp current source, I need to tell LT Spice to make it a 1 amp source. So with my mouse over the current source itself, I'm going to right click, okay? And I can just type in a DC value, which is going to be 1 amp. Before I do that though, I want to show you guys some other things. If I click this advanced button, it gives me a whole bunch of options, many of which we're going to wind up using throughout this class, okay? So the same current source model is used for all of these different things, okay? So I could use it as a DC source. I could use it as a pulsed current source, meaning that it has a specific height value of the pulse where I define what that height value is, how long it takes to go from off to on, how long it takes to go from on to off, how often it repeats itself, and the number of times that it repeats itself. So I can do just a series of pulses using the pulse current source. I can choose a sinusoidal current source where I get to define what DC offset, if any, it has, the amplitude of the current source, the linear frequency of the current source, not the angular frequency, just the linear frequency. If it's delayed before it turns on, what the phase angle is, and the number of cycles, okay? I can also do an exponential current source where I let it know what it is initially, what it is when it hits its peak value, how long it takes to rise, how long it takes to decay, all of that kind of good stuff. And then the delay for the rise and the delay for the decay. I don't remember what SFFM stands for off the top of my head. It has something to do with modulation. Um, I've never actually used this one, but it's available. Then we have PWL, so that's piecewise linear. So we can just essentially play connect the dots, um, saying, the current has this slope over this interval, and then it's this other thing, all of that kind of stuff. We can also upload a file, so an Excel file that has all of that information in there for really complex piecewise linear functions, or we could introduce a table as well. Okay. So those are all of the different things that we can do on the left-hand side. Then on the right-hand side, we can just make it a DC value, or we can do small signal AC analysis, which we'll do much later in this class when we talk about filters, where we give it a specific amplitude and phase, but the frequency is allowed to change. Okay. So lots of different things that we can do this. I'm just going to go back to the DC value now and just type 1. I don't need to put a unit on this. It's automatically in amps unless I tell it otherwise. Okay. Damn it. I need to click none there so that it doesn't do that thing. And do 1 here. Sorry about that. Okay. So now it is a 1 amp current source. Okay. Let's see. So in parallel with that guy, I had a resistor. So I can literally just click on this icon. Let me move this damn thing out of the way. I can click on this icon that looks like the schematic symbol for a resistor, or I believe I can just press the letter R on my keyboard. Nope, that didn't work. Oh, maybe I just didn't press it right enough. Yep, there we go. Okay. So R brings up a resistor. So I'm just going to place that on here somewhere. I've got a couple of other resistors to place. So I'm going to go ahead and do that. So I'm going to do that other resistor out here. For the one that's horizontally oriented, I'm going to press Control R, which will rotate the resistor. And I'm going to drop that guy down here at the bottom like so. Those are all of my resistors. And now I'm going to start, actually, let me do the voltage source next. So for the voltage source, I can just click this button that says voltage source. I can type the letter V, or I can go to the component menu and type the word voltage. All 3 ways get you the same result. I'm just going to click V. I need this voltage source such that the positive polarity is on the right. So I'm going to press Control R, and now it's rotated 90 degrees so that the positive polarity terminal is on the right. I'm going to put that here. I have the exact same options for the voltage source as I had for the current source. So I'm just going to right click on this guy and tell it that it's a 12-volt source. I'm not going to re-explain all of that other crap. For the resistors, if I just put my mouse over the resistor itself and right click it, I can tell it what resistor value that I'm going to use. So this is going to be a 6 ohm resistor. I can actually include tolerance information. So if I say that it's a 1% tolerance, it will randomly choose a 6 ohm resistor plus or minus 1% each time I run the simulation. I'm just going to leave it blank. I can also give it the power rating so that if I chose, let's say, a 1/8 of a watt resistor or something like that, like I might put in a physical circuit, I can see whether or not it would burn out that resistor when I simulate this circuit. For what we're doing right now, I'm just going to leave those blank because I just want to treat it as an ideal 6 ohm resistor. Okay. And I'm going to go ahead and make these other guys 6 ohm resistors as well. So the last thing that I need to do here is just wire all of this stuff up. Okay. So this, damn it, this thing keeps getting in the way. So this option right here is for wire, or I can just press the W key. So that's usually what I'll do. So I'm just going to click on this terminal of the current source and then start moving my mouse around, and it's going to let me run wires to different places. And then over here to the right, I'm just going to put like kind of a stub of wire so that I can define my terminals. Just like I had in my original schematic diagram. And make that look a little nicer for you all. Okay. So the last thing that I'm going to do before I try to simulate this circuit is I'm going to label some networks, okay? So I'm literally going to label terminals A and B like I did earlier. So I'm just going to put an A right here. For what it's worth, I'm clicking on this button that just says net above it, label net, and then typing in the text that I want. And then just putting it on the schematic diagram wherever I want it. So I believe we can all agree that this at least looks like the circuit that we started with. Okay. So now what I'm going to do is I'm going to try to simulate it. And for what it's worth, I am expecting an error. And I want to talk about that error in just a moment. So I'm going to click on this button that has a gear and says .ac. So this is the simulation command. I could also click on the simulate thing and go down here to where it says configure analysis. It's the same thing, okay? So I have lots of different options here. So transient analysis is how I look at a circuit as it changes as a function of time, okay? This is a DC circuit, so it's not really what I'm looking for. AC analysis is looking at a circuit and seeing how it changes as a function of frequency. We're also not doing that, so I'm going to move along, okay? Then we have a DC sweep. So this is a way for me to run multiple DC simulations in a row where I sweep the sources. So I might make it be like 1 volt and then 2 volt and then 3 volt and so on and so forth. I don't need to do that for this one because I just have fixed sources. So I'm going to keep on moving. Then I have this noise thing, definitely not doing that. I have this small signal DC transfer function. This is more for transistor circuits, not what we're dealing with here. I'm actually looking for a DC operating point simulation, okay? So this is the one that I'm going to choose. And I'm just going to drop this thing that says .op somewhere here, and then go on about my day. So that's what's telling the thing to do the DC operating point simulation. Now I'm going to press this big green play button, and it gave me an error. So it says the circuit does not have a conduction path to ground. Please flag a node as ground. So essentially, LT Spice is always doing nodal analysis. Can't do anything else. So we have to tell it where ground is, okay? It's our choice. So I'm going to choose to put ground in the exact same place I put it earlier. What happened?
Text box appeared.
A text box is supposed to appear.
And I got an error too.
So some of us got errors and some of us didn't. Very weird. Well, I was expecting an error, but choosing ground is going to be relatively important. So like looking at what you have right there, if you look at where it says V open parentheses B, 4.43179 e to the minus 25. So that's 0. So it's treating node B as if it were ground, essentially 0, and it's measuring everything else with respect to that. But if I literally tell it, hey, node B is ground, instead of giving me that weird number, it will actually give me 0. So it says the voltage at node 1, which I don't know where the hell that is -10. We'll sort that out in a moment. The voltage at node N002 is -2 volts. We'll figure that out in a moment, but I'd be willing to bet that based on our nodal analysis, we could probably figure out what those are. The voltage at node A, the one that I labeled specifically as A, is 2 volts. And then it also tells me the information, the current flowing through current source labeled as I1 is 1 amp. The current flowing through the resistor labeled as R1 is negative 4/3 of an amp. The current flowing through resistor R2 is 1/3 of an amp. The current flowing through resistor R3 is 1/3 of an amp. And the current flowing through the voltage source labeled as V1 is negative 1/3 of an amp. I'm going to try to do this. So I'm actually going to X out of this thing real quick here. So this text window, because all of that information is now available on our schematic diagram as well, okay? So if I mouse over this node A, which is the positive polarity terminal of my Thevenin voltage, down here in the bottom right, it tells me the DC operating point is 2 volts. So that just told me that the Thevenin voltage is 2 volts. Well, if I mouse over any of the elements, it's actually going to tell me how much current is flowing through that element, as well as how much power is absorbed by that element. So our voltage source here is absorbing negative 4 watts of power, which means it's supplying positive 4 watts of power. If I mouse over this particular resistor, it's telling me that the current flowing through it is negative 1.333 and change amps, and the power dissipated by it is 10 2/3 of a watt, et cetera, okay? So all of that information that was in that text file is now actually accessible on the schematic itself if we put our mouse in the right place. So when we put our mouse on a node, it's going to give us voltage. And if we put a mouse on an element, it's going to give us current and power, okay? So we did our Thevenin voltage simulation. We got the 2 volts that we expected and our other nodal voltages. So node 1 is this one here to the top left. It tells me, by the way, at the bottom left side of the screen, this is node N001. So it's telling me what that is. Yes. Oh, hot damn, I genuinely didn't know that. My old version of this didn't do that. That's neat. Good. So clicking on the nodes or mousing over the nodes gives you voltages. I wonder what happens if I left click on this source. Jack shit. Okay. So, but mousing over the sources tells us current and power. So let's figure out how to do the Norton current real quick, since this simulation agreed with what we got for the Thevenin voltage. So for the Norton current, I just need to short these terminals together. So I'm going to run my simulation. Sorry. It's giving me this stuff, but I run into a little bit of a problem because LT Spice treats these wires as part of the same node. So I can't really find the current that's flowing through a wire like this. So I have to get a little creative, okay? Now, one thing that I could do is throw a resistor in there and just make the resistor incredibly small, right? So if I put like a 1 nano ohm resistor in this circuit where all of the other resistances are 6 ohms, it's going to treat that like it's really close to 0, and it's going to give me an answer that's really close to what I would expect. A smarter way to do it would actually be to put a voltage source there, because I can just put a 0-volt voltage source, which is what a short circuit really is in an ideal circuit. And that gives me an actual element that I can measure the current through while forcing it to behave exactly the way that I want it. So I'm just going to type V here, literally just drop a voltage source on top of this wire, and it will break it and insert it where it needs to be. And then I'm just going to right click this and put 0. Rerun that simulation. And now when I mouse over this guy, it tells me that my DC operating point for this is 500 milliamps or half an amp, exactly what we got. Now, one limitation of the DC operating point analysis is that it doesn't give us directions for our current. So we kind of have to infer them. So instead of doing a DC operating point analysis, I'm going to delete this little spice command here, and I'm going to have it run a transient analysis instead. So I'm just going to go back to this. Because it's a DC circuit, I'm just going to tell it to stop the analysis after 1 second. I'm going to leave literally everything else blank. So if you press the delete key, it brings up some scissors, and then you click the scissors on whatever it is that you want to delete. So I'm going to run this simulation real quick, and it pulls up a blank plot. Okay, so the transient analysis is telling us how the thing is behaving as a function of time, but I need to tell it what I want to look at. So if I wanted to look at the current flowing through this guy, I would just mouse down here. Notice now, let me get rid of this thing. So now that we've ran a transient analysis, when I mouse over a node, it gives me a voltage probe icon, okay? And it tells me down at the bottom, just like it did earlier, what the DC operating point at is. So the DC operating analysis is actually buried in the transient analysis anyway, okay? When I mouse over an element, this is a current probe, okay? And the arrow is the direction that it's assuming the current is flowing. So the current flowing down through that 0 volt source, which is what I'm actually interested in, is that 500 milliamps. If I click on this, it's going to plot 500 milliamps as a function of time, which of course looks like a straight line because it's a DC circuit and it doesn't change. So realistically, running the transient analysis and then just closing out this plot window gives us the same information as the DC operating point, except that, well, shit, I guess I needed the plot window open for it to tell me the direction of the current and all of that kind of good stuff. Okay. All right. When's this class end? 1:45. All right, I have 23 minutes. So let's do a ridiculously easy transient analysis problem real quick. So I'm just going to close these things out. And we're going to work another ludicrously simple example. Okay. So let's say that I have the following circuit. I have a switch opening at t is equal to 0 seconds, a 10 volt source. Let's throw a 10 ohm resistor here. A 5 ohm resistor here. And then a 25 millifarad capacitor here. And I'm interested in finding the voltage drop across the capacitor as a function of time. Okay. So at t is equal to 0 minus, our switch is going to be closed and we're at DC steady state. So our capacitor is going to look like an open circuit. So this is the circuit that we're actually analyzing. A 10 volt source connected to a 10 ohm resistor. Here's a 5 ohm resistor. Don't know what the hell is happening. Literally touching nothing. There we go. And this is VC at 0 minus. Who can tell me what that's going to be? 10 volts. Yep. All right. At t is equal to 0 plus, our switch is open, so our 10-volt source is essentially disconnected. I guess now that I'm thinking about it, we don't even need to do this analysis at all, but I've already started, so I'm just going to keep on doing it. Replacing my capacitor with a voltage source that has the same polarity and magnitude as VC at 0 minus, because we know the voltage drop across the capacitor cannot change abruptly. We're going to see that VC at 0 plus is still 10 volts. So anyway, since our source is disconnected, everything at infinity is going to be 0. So we're just dealt with a simple natural response problem. What is my time constant going to be here? What's REQ for this circuit? 15 ohms, because we would disconnect the capacitor and look in through the terminals of the capacitor at the dead network during the transient condition. So that would just be 5 ohms in series with 10 ohms. So 15 ohms. CEQ is quite obviously 25 millifarads because it's literally the only capacitor available. So just for what it's worth, we take this guy out, looking in through here with that guy turned off. Yep. So 15 times 25 is a number I probably should do in my head, but I can't. 15 times 25, 375 milliseconds, I believe. So from this, VC of t is going to look like 10 volts for t less than 0 minus, and 10, let's see, e to the minus t over 375 milliseconds volts for t is greater than or 0 plus. And I'm going to make this part look a little bit nicer. So 1 over that is the same as 2.667 and some change t. So the reciprocal of 0.375 is apparently 8/3. Yeah. 0.375 is 3/8, so 8/3 makes sense. Okay. So all of this to say, we can simulate this circuit in LT Spice as well. And we're going to be dealing in this class not with RL circuits and RC circuits, but RLC circuits, right? So we're going to have 2 energy storage elements, so they're a lot more complicated, okay? We can use LT Spice as a tool by which we can check our analytical solutions to make sure that they're right. So I can simulate the circuit and put in my solution and see if they match. So I'm going to make my circuit really quickly here. And I'm just going to make my circuit at t is equal to 0 plus, okay? So here's my 10-volt source. Here's my 10 ohm resistor. Here's my 25 millifarad capacitor. So I'm just going to do 25 M or millifarad. I'm going to wire stuff up. So this voltage source during the transient condition is open circuited, so that's why I'm leaving it open over there. I'm going to choose to define the negative polarity terminal of the capacitor voltage that I'm interested in as where I'm putting ground. And for simplicity's sake, I'm going to label the positive polarity terminal of my capacitor voltage as VC. So I'm just going to put that up here. Okay. Oh, I forgot it. That's on me. I just totally forgot it. So good catch, Ashton. Yeah. Okay, so there's our circuit. So because we're starting our analysis at essentially t is equal to 0 plus, we need to tell the circuit what the initial conditions were before the switch opened. So I'm going to do that by putting in a SPICE directive. So this thing here where it has .t, I'm just going to click on this and it's going to open up a text window. And what I'm going to do is I'm going to do .IC. So that is initial condition. Okay. Then I'm going to do V. So I'm defining a voltage and I'm going to do VC. So that's telling me, or that's telling the computer, hey, set the voltage at that particular node, which is the positive polarity terminal of the capacitor, to some value. And I'm just going to tell it 10 because that's what our analysis told us. Okay. So it's starting the simulation under the constraint that the capacitor initially has a 10-volt drop across it. I'll let you guys catch up before I click OK here. Yes. So that is the voltage at node VC is equal to 10. Now I'm going to press OK and just drop this literally anywhere. And then I'm going to set up a transient thing. Okay. So since our time constant was 375 milliseconds, and I know that it takes roughly 5 time constants for things to decay, I'm just going to do some really lazy math and say 375 milliseconds is close to half a second. And since I want to wait 5 time constants, I'm going to run this for 2.5 seconds. Okay. That should be enough time for me to see the system decay down to the capacitor being fully discharged. Dropping that anywhere and then just running my simulation. And so what I'm going to do now is I'm just going to click on this node since I'm interested in the capacitor voltage, and it's going to give me the capacitor voltage as a function of time, exactly what I would expect. Okay. So it starts at 10 volts and it exponentially decays down to 0. And now what I'm going to do is with my mouse over this plot plane, I'm going to right click and I'm just going to put add trace. Okay. So I could choose any other quantity to plot here, or I can type in an expression. So what I'm going to type in is literally the solution that we came up with a moment ago. 10, go for it. So with the graph open, I right clicked and then I clicked add traces.
Probably go to it comes up with this. Yeah, it doesn't drop down.
Oh, let me.
I don't know if it's like the shortcut. That's the play. The other one, the wire. Oh, right here. Yeah, I think that's oh. Let's see what. We go to, I don't remember.
You don't know.
Oh, yeah.
Oh,
And that was just your whole sort
oh,
of.
jeez.
Yeah.
Bro, that was like the go thing.
Okay.
Yeah.
So last thing I'm going to show you guys for today, I'm literally going to type in the mathematical expression that we came up with, right? So I'm going to do 10 multiplied by exp, open parentheses, negative 2.667 multiplied by, and I have to literally write out the word time here. I'll let you guys catch up if you're interested before I click OK. All right, I'm bored, so I'm clicking OK. So what happened is this blue curve, which was our analytical solution, pretty much completely overlapped the green curve. What does that mean? They're the same thing, right? So according to this computer, we must have done our analysis right because our analysis exactly matches the simulation, okay? Now, this was a ridiculously simple thing, but you could imagine that for more complicated circuits, this is a really good tool to have to check your work, which is how you're going to use it once we get to that part of the class. So I just wanted to kind of introduce that to you. All right. I have taught 3 classes straight. I'm starting to lose my voice, so I'm just going to shut the hell up.